It says we have an excellent connection. And I believe that we are live. So welcome everyone. We've taken a couple of weeks off from our FRC workshop series. I hope you've enjoyed having your Monday nights back to yourself. But we're really, really happy to have another workshop tonight. So we want to welcome Evan and Ollie from Team 3132. And they are going to be talking about shooters tonight. So hope you're all ready for a great and interesting discussion. And I will turn it over to Evan and Ollie.
Awesome. Good evening, everyone. Yep, so I'm Evan.
Hello, I'm Oliver.
Unfortunately, Dave couldn't join us tonight because he's getting married. So we hope that's a good enough excuse. So generally, the idea of the presentation is this is how you build sort of your first shooter, or maybe your second shooter. It's really a lot of the content we've written in the slides is really aimed at you're just getting started. However, I think we're both really happy to answer much more in-depth questions if there are any, or go into more detail about anything in the slides. So feel free to ping questions sort of whenever, and we'll try to fit them in as we're going. Or if there's something that you get really interested about, or you can think of a question for immediately, feel free to just shoot it through. All right, so the general outline for tonight. We want to start off by actually talking a little bit about game strategy with shooters. We think this is really important because it can influence your design quite a lot. We're then going to go into the hardware of shooters, so how you build them and generally what shapes they take, what sort of components go into them. Then talk about electrical, a little bit about the motors you might use and the sensors you might use and why you would pick those. And then some about software. This is largely around control systems. And then at the very end, we're going to wrap up with quick prototypes. So what's the sort of the path of least resistance to getting to a working shooter? So let's kick off with some game strategy.
Yeah. So the first kind of thing to talk about when considering a shooter is where on the field you want to shoot from. Having said that, maybe the object's the first thing you think about, but we're assuming that's a given for each year's game. Where you're shooting from the field is pretty important because it dictates kind of how you might align the shooter if you need to use any kind of advanced targeting or a driver alignment, for example. And so we're kind of going to encourage you to be thinking about aligning to the physical objects on the field. For example, the pyramid in the bottom image, you can see that provides a nice flat reference surface to drive your robot up against. So you know exactly where your robot's pointing every time you want to shoot. And that's a really powerful thing to do as a robot that's attacking, because you can't really be defended by being shoved. So the defenders have to have a much more cognizant strategy, and they need to be thinking about that ahead of time to build some kind of thing to get in the way. If you're in a nice safe zone or pinned in a corner somehow, then that's really excellent strategy, and that helps define where your shooter on your robot's going to be and what kind of shooter is most appropriate. For example, if you want to drive up against the wall or underneath the goal and fire up in that, you might want to push your shooter to the very back of the robot, which will define what kind of shooter you can use. We've also got some points here about the trajectory you might want to consider. A curvy trajectory might seem like the obvious thing to do as a STEM student. However, what we would encourage you to do is think about what happens when you flatten that parabola out to the point where it's effectively a straight line. You basically get a dead straight dart to go straight into the goal, and that means you don't have to do any kind of distance calculations or any kind of angle calculations other than just point your shooter at the goal. And that makes the whole process much more simple and typically more accurate as well, because we can apply more power, which we'll go into later.
Yeah, and the reason we really wanted to start with this is because you can very often make your life much easier or much harder depending on how clever you can get with your game strategy. If you are really good about aligning off of physical points and picking trajectories that are easier for your shooters or sort of more consistent, you can very quickly make the problem a lot easier for yourself. So it's really important to spend some time thinking about this because it will definitely flow on through the rest of the design.
And we'll come back to this as we go, talking about how these decisions might factor into later design choices.
Yeah. All right, with that, let's kick off with some hardware. I'll clear that little drawing you made. So we sort of look at shooters in two big categories. There's obviously little variations that go into these, but largely you can divide shooters into sort of two, or FRC shooters into two categories. So one of them is what we kind of call a two-wheel, quote unquote, shooter. Generally, it's when a shooter propels objects with sets of opposing wheels or opposing moving objects simultaneously. So I have a couple examples here. One of these is from 2012, a game where you're firing little basketballs, foam basketballs, quite soft, and then 2016, which was Stronghold, if either of those games are ones that you might know. And in each case, you see there's two sets of opposing wheels. So some of the pros to this design is it's really easy to build. So you can see in that second picture, that's something that's very few components. It's really nice and simple. And you can sort of throw it together really quickly and get a pretty good shooter, something that can at least do a decent job of shooting the game element. They're also much more power efficient than the second design we're going to show you because you are spinning both contact surfaces. Sometimes if you design it this way, you can actually get it to double as an intake as well. So if you sort of think about if any of you were around in 2018 where we had the yellow power cubes, there are a lot of robots that were able to have two sets of wheels swivel down, intake the power cubes, or sort of like cubed big plastic crates, and then pop them into scoring areas, all with the same two wheels. And as we were just talking with before, it also works with non-round game elements. So if you have like totes or big cubes or that sort of thing, this design still works the same. It's really good for that. Now there are a couple cons that are a bit difficult to describe. And the first one is something that I've come to know as the knuckleball effect, which is sort of a baseball reference. But the general idea here is that when you fire a ball with no spin, so let's say it flies directly straight, it's not spinning at all, you often get what in baseball is called a knuckleball pitch. And essentially what it means is you get sort of funny motion on the ball, you get unpredictable motion. It's difficult to describe or to sort of conceptualize, but I'd encourage you to go out and try it with a ball. Try to throw a ball with the least spin possible. And you'll notice that it tends to do funny dips or funny turns that you don't expect. And so it can really decrease the consistency in the way that round objects sort of fly through the air. So generally, spin is really useful there.
This is far more pronounced on a large, soft object than a baseball. You can see it on a baseball, but you have to be trying pretty hard.
Yeah, this is also something you probably Google and get a pretty good idea for. So that's one of the cons. The other one is trying to match speed between the wheels. You can sometimes get issues where if you have one wheel going faster than the other, the ball sort of comes out at an angle, or it gets more spin or less spin than you're expecting, or something like that. So there's a bit of an art to trying to either make it so the speed being matched doesn't matter that much, or getting it to match pretty well. So that's something you just have to keep an eye on when you're designing shooters like this.
We will refer to these as linear shooters throughout the presentation as well, but that also includes other variations on it. But yeah, it's just so if there's any confusion, linear shooters, kind of, this is what we're describing.
The second one is one that I think you'll probably see more often in FRC, and it's what we know as either a one wheel or a hooded shooter. And this is where the shooter propels round objects, so you can only really use round objects here, with wheels opposing a static surface. So in the two examples here, we have this shooter, I think is actually a prototype I pulled from somewhere online from this past year, from 2020 with the foam balls. If you look at pictures of these, they very often look quite the same. A lot of hooded shooters will end up looking very similar regardless of the actual game element you're propelling, except for this other one. I pulled this second picture I thought was interesting. This was a Frisbee shooter. So you can sort of imagine a Frisbee sitting in this area here and being propelled sort of around the back of this arc. So in this case, a Frisbee is actually round and we're able to fire it this way. Works quite well. So pros to a one-wheel hooded shooter, it's much easier in general to achieve consistency. However, there are some downsides that I guess we'll get into. The other really interesting thing about one-wheel or hooded shooters is the spin that you put onto the game element. And that spin actually ends up being advantageous for both the trajectory you're aiming for, but also keeping it in the goal. What do I mean by that? I think the best way to describe this may be a drawing.
Yeah.
Okay, how about I'll start drawing. Ollie, do you want to keep talking through the pros and the cons?
Yeah, I can have a, yeah, okay. So the more compact point here is both literally it's more compact, but it also typically gives you more packaging options. And what we mean by packaging is the way you can fit the shooter or the mechanism into your robot. A hooded shooter, because you can change the direction the ball is going in the process. If, for example, like I was talking about, shooting from pressed up against a wall, you want to shoot from the very back of your robot, you can have the ball come through your robot and then change direction at the back and then go forwards again, which gives you a better angle on that goal. Whereas if you're doing a two-wheel shooter, typically they're firing from the front of the robot, which means that you don't really have the same flexibility there. Obviously, both of them can do kind of anything if you try hard enough, but there's more, yeah, you have to try a bit harder to make it work. And the same with the compression here. It's a bit easier to make a system that is squeezing the ball harder. We go into much more detail on compression in a few slides time. And basically the reason you want compression is to be able to impart the momentum of the wheel onto your object you're firing.
Yeah, so let's talk through this drawing here. So often when you're making a hooded shooter, you get this backspin where the ball is sort of, or the element is sort of spinning this way when it hits the goal. This can be really good for two reasons. The first one is backspin will make a overall flatter trajectory. So if you imagine an actual parabola, when you put backspin on the ball, rather than traveling on a real parabola, it tends to sort of flatten out, which is useful for trying to get into a goal that's sort of vertical. The other reason this is really good is when you imagine when the ball hits the sort of backboard of the goal, the spin will direct the ball down.
Same with the top lip.
Yeah, so the ball can hit here and it'll sort of get directed that way. So this is really good because very often with this trajectory, you end up either slamming to the back wall or hitting the top lip. And in both cases, the spin will actually help quite a lot in directing the ball down into the goal and reducing the times, basically reducing the chance that the ball bounces back out.
This is absolutely the same principle you see with someone doing a free throw in basketball when you want to put backspin so it bounces off the backboard into the goal a little bit nicer.
Yeah.
Into the hoop.
So what are some cons to the one-wheel shooter?
It's drastically more complicated to make the first version of, and that's kind of the biggest one. You can get away with making it by hand, and we have some a description of how you might do it at the end. But typically, because of the way you need to make a curve, it's much easier to do it with a laser cutter or a CNC or something like that, because it lets you make a much more consistent curve, which is just a little bit more.
I guess just straightforward.
Yeah,
and it's more consistent.
Yeah.
It's a good example is this picture on the left. This is a laser cut prototype, and it's the kind of thing that's much faster and is going to be consistent. Whereas by hand, you might find that you have some inconsistencies just by your manufacturing method.
Yeah. And the compression of the power, it's kind of obvious because you've got the ball or the object sliding / rotating on the back surface, you're going to have some friction there, and there's going to be some resistance. So obviously, you're going to be putting power into both rotating the ball and propelling it, not just propelling it like in a linear shooter.
Yeah, and also compression. The more compression you have with a hooded shooter, you'll see drastically more power required to make it shoot. So those are the sort of two general kinds of shooters that you can build. We kind of want to now go into what we're calling design decisions. So what we mean by that is, what will you change and test with a prototype? What are basically the main points of a shooter? What differentiates one shooter from another, and what are the most important things to get right? So we have 6 here that we're sort of going to go through with you, starting off with one of the most important: wheels.
I reckon that between 4 and 5 might be a good place to grab some questions. So we'll make that. We'll say that when we get there. But yeah, if you have any questions, feel free to post them.
Okay.
Want me to do wheels?
Yeah, go for it.
Excellent. So wheels are, I think, every FRC team's favorite thing to test. It seems to be forever testing wheels on intakes and shooters. And I think something that we will stress up front here is it often doesn't really make a lot of difference if you're doing kind of your first couple of versions of a shooter in what wheel you use. 4-inch wheels, as we said on the slide here, 4-inch wheels are a great place to start because it gives you, you usually have enough power with a simple setup with 2 motors or something, and it's easy enough to adjust that. If you use a bigger wheel, you're starting to end up with a much larger physical volume for your mechanism, and it just gets a bit more messy when you're trying to fit that in your robot. One of the biggest hints we can give you is that the harder the element, the softer the wheel, and vice versa. So if you're shooting a solid wiffle ball or something, they're hard plastic. You want to use a soft wheel to be able to conform to that to the shape and actually grip it. And the other way around, if you're using a really soft ball like this year, you want to use a harder wheel. And the reason you don't want two, like a soft object and a soft wheel, is basically because then you have 2 different things compressing. So it's really hard to predict the actual diameter of what's spinning. So you end up with varying diameters and things like that. We got a few suggestions here on types of wheels, but the one we're going to stress, and as you'll quite clearly see here, compliant wheels are not suitable for shooters. And the reason for that is they actually grow in diameter the faster you spin them, because they don't really have any structure holding the outside in. And so that's going to cause all sorts of grief right up to the point where they explode and potentially cause some pretty serious damage. There are other types of rubber wheels which can also do that. So pneumatic wheels probably won't explode, but might actually deform and change shape a bit, which will vary the diameter and make it difficult to predict what's going on. But yeah, you need to be aware of that. And when you're buying wheels, there's often an RPM rating that is given, like a maximum. So you want to just be aware of that if it's a rubbery kind of wheel. A white brick wheel like that has an RPM.
Yeah, and we've also given a couple of good recommendations here that are just good starting points, or really ones that we often gravitate towards. Yeah. One of them is actually the white high grip wheel. So this is the same tread that comes on the kit chassis. Those will be 6-inch wheels. You really want probably a 4-inch wheel if you can get it, but that tread's actually totally fine. The other one is, they're called Coulson wheels. You can get them from Vex. They'll often have
the image. Should I show them?
Oh yeah, that's a good idea. It's over there. So here's a Coulson wheel in the left image. They're very good generally because they're just consistent. They wear very evenly and generally don't wear that a whole lot. They strike a good balance between how much friction they have, I guess, on most game elements and the way that they wear. And often because of that end up being just a pretty decent choice. It can be spun as fast as you like. So so those are 2 good options that we can almost always recommend for almost any shooter. Next thing to think about is compression.
Yeah. So as we kind of alluded to before, Compression in this context is basically how much you're squishing the ball between the wheel or the wheel and the back, the wheels or the wheel and the backboard. And basically what's happening as you squish it, you're giving the wheel a better chance to impart its energy, its momentum into the ball you're trying to fire, and actually accelerate that ball. You basically, the more compression, the better the power transfer, but you also have to have more power in your system to overcome the added friction and stresses, and you're more likely to have things bend. And it's definitely possible to overdo compression, both to the point where you stall out your system and where you start breaking stuff and damaging game elements as well if you're not careful. If you don't have enough compression, typically what's going to happen is you won't actually kind of see the ball and the wheel rotating together. They'll start slipping and have sort of dynamic friction there, and that's going to not have as good effect at transferring the energy, and you're more likely to rub like scuff the balls and things and rip the covers of soft balls like this year.
Yeah, that's a good point. If you're starting to see like big scuffs on your game elements, it's probably because you're actually slipping when you're shooting them.
Yeah, and obviously there's always going to be a little bit of slip because you have to accelerate the object, but the question is, how much? We've given some pointers here. 1 inch of compression in a soft element is pretty good. We were discussing for varying diameters, it's something like 1/5 of the diameter of the object is a ballpark number to start with. And if it's a hard object, you're probably wanting, it's more about the feel at that point, but 5 to 10 mil of compression in the softer wheel is probably appropriate. But that's one that you just got to play with, as we said below. You should be able to push the ball or the object through the wheels, and you should have to try, but you shouldn't be really having to force it or seeing anything bend out of shape to be actually able to fit it. That's too much compression if you're deforming your whole structure to make the object fit.
Yeah, and with every, I think with a lot of the slides here, it's going to be sort of a feel thing. So we can give you some pointers here, but in the end, it's going to be just testing it and seeing what you think works better and what doesn't. The next thing you can sort of play with that ends up going sort of hand in hand with compression is contact time. So what do we mean by that? We mean how long the element is in contact with the driven wheels. So if we're talking about like a hooded shooter, for example, we often talk about the wrap, which is essentially the degrees of contact time where the element is in contact with both the hood and the wheel. And in a linear shooter, you might have how long the linear shooter is. So if you have quite a long linear shooter with maybe multiple wheels, which we also will get into, you will have longer contact time. But the big one that this plays a part in is what Ollie is drawing here, which is sort of a hooded shooter and how many degrees. You can imagine the change in degree from the start of your hood to the end of your hood, like that. That'll be how many degrees of wrap you have, which is quite important. And the whole idea here, the whole sort of thing we're going for is we want the element to experience less momentary acceleration. Momentary acceleration often means slip, and it often means less consistency. So anything we can do to sort of decrease that momentary acceleration, we really want to do that. So more contact time, more consistent, and it's almost always preferred over more compression. So you can sort of substitute more compression by just having more wrap on your shooter or more contact time.
Basically impulse, right?
Yeah.
You're trying to reduce your impulse as much as possible. So by smoothly accelerating the object, you have a much better chance. And that'll factor into the next point we'll bring up. But yeah, the smoothly accelerating is what you're trying to achieve here, rather than punching the ball through your shooter. Yeah,
and often the almost only downside to more contact time is it's larger.
Yeah.
So if you can fit it in your robot, it's almost always worth it. So where's a good starting point for wrap? If you're talking about hooded or one-wheel shooters, really aim for a minimum of 60 degrees. And that's sort of pushing it. Aim for over 90. If you can get over 90, you should have a pretty consistent hooded shooter.
If you have like order of 60 degrees, you're very likely going to need to have some sort of significant flywheel and inertial system, because you need to impart that energy so quickly. that it's going to have to be the wheel is going to have to be rotating very quickly and very consistently.
Now, let's say you've gone for either a linear shooter or a two-wheel shooter. These actually end up being a bit different. We'll talk about in the next slide. But yeah, as a general point, you can almost never have too much contact time, and you know you need more when you're still slipping on a game element, even after you've added a bunch of compression. So what was the other thing we were alluding to? That's run-up wheels. And generally what we mean here are just extra sets of wheels that are sort of running at a slower linear speed. So if you think about the linear speed on the outside of the wheel, you can have extra sets of these that sort of slowly accelerate the ball up to its final velocity.
Yep. In a linear shooter, sometimes you'll have two sets of final wheels per se, which effectively extends the contact time. But also, if you might have one set of wheels that is 90% of the final speed of the and then 100% of the final speed with a simple belt reduction between the two or something to facilitate that acceleration more gently. Yeah, that's all to say there.
Yeah.
If you can fit more if you can fit run-up wheels on your robot, you really should. Oh, the other thing I don't think we mentioned here is by having run-up wheels, you kind of give a defined input, like an input velocity to your shooter, which will dramatically change the output velocity. If you can imagine, if you had a big hopper of balls bouncing around, some balls might jump into your shooter more quickly than others. Whereas if you had a wheel that's always rotating at the same speed, it kind of defines how fast that object's going to be traveling. Which is, I think, a good point here. You should never have any slip in run-up wheels. That defeats the whole point. They're not run-up wheels at that point. They're an internal shooter or something.
Yeah. So having that sort of consistent feed from your shooter or your run-up wheels also helps a lot with control system down the line. If you're struggling to get your control system to be consistent, easy way to help out with that is to make the problem more consistent. So in other words, having a more consistent velocity coming into the sort of final shooter wheel.
It's not uncommon to tie your run-up wheels with your shooter wheels with reductions and then run it all off the same motor, because it adds inertia to the system, which can be beneficial if you're trying to shoot multiple elements at the same time. And then it just simplifies the process and makes sure that if you identify like a ratio, say you want the input wheels to be 60% of the final speed, you can lock that in. You don't have to deal with that in code anymore. Yeah.
Another really good point here is that run-up wheels will often actually be even more consistent from shooting than you can get with sort of wrap and compression. And we saw this a lot with this year's game elements. So the balls this year were very, very sticky and changed quite a lot over the course of sort of using them. Additionally, they all had somewhat different compression out of the gate. So we found that by adding A, more contact time, but B, more sets of run-up wheels, you could more consistently fire the balls from this year because you weren't relying so much on either how sticky they were or how much they compressed or didn't compress.
And I suppose something to note on this when you're testing your shooters is to be cognizant of the velocity you're putting the balls into the shooter. Because if you're having different people push them in at different speeds, you're going to have different kind of distances. And if you are pushing your ball in really hard into the shooter and you're like, wow, it's going super far, and then you put on the robot and it's just not performing as well, that's a sure sign that you need some run-up wheels in your system, or you kind of were simulating run-up wheels when you were prototyping.
Yeah, and again, this is really similar trade-offs to the contact time. It's really just space and sort of weight on the robot, and potentially the number of motors, depending on how you design it.
It's not uncommon to see wheels as actually like belts, or like polycords or something like that. But yeah, I think the next one's motors. So if there's any questions, now might be a good time. Questions, people?
Yeah, we'll take a short pause because there's a bit of a delay.
Yeah.
See if we grab any questions.
So both of you have been doing FRC for quite a while, yeah?
It's been a bit.
Yep.
Yeah, how many years?
So my first game was 2012.
Mine was 2013. So
So I guess one of the questions that's come up is with everything that you've talked about, and maybe you want to think about this for the end of this workshop, but it would be really good to hear from you as to which robots you think people should look at from previous years to see different kinds of shooters. So have a think about that, and maybe we can come back to it at the end of the workshop.
Yeah, okay, that's really good.
We do have another question that's come in. How much time do you typically spend in planning before you start prototyping your components?
that's a really depends on like your team's ethos almost.
Yeah.
But yeah.
We often spend at least a full day not doing anything with prototyping, just thinking about where we might want to shoot from and sort of what gameplay we expect to be working with. Coming back to that very first slide, if you don't have your strategy locked down, it makes design way more difficult. You can often make you give yourself a much harder problem than required. So yeah.
And kind of as a mentor, often I don't particularly care what kind of shooter we use. I pay far more attention to where we're shooting from and to using the field to our advantage, and trying to simplify the whole process in that, you know, if we can not use vision tracking, which we'll come into later, you know, we absolutely shouldn't use it. So yeah, maybe we'll move on to the motors now.
Yep, let's hop on the motors. So sort of the next big design decision you'll have to make with your shooter is what motors and how many motors you're going to put onto it. As a rule of thumb, we've put down sort of two general solutions here. The simple solution is really just sim motors. So these are the same motors you'll be using on your drive. They come in the kit of parts. Or if you have them or can get them, mini sims are also really good here. They have the same RPM, just a bit less torque, and generally that's fine for shooters.
It turns out that around 6,000 RPM is a really good number for shooters, and that happens to be the speed of a sim, so it's quite convenient.
At 4 inches.
At 4 inches, yes, yes.
And really the only downsides here, they're pretty heavy. They're pretty heavy and big. But often that, if this is your first shooter or maybe your second shooter, that often isn't a problem. And so the sims can be a really good choice there. I mean, they're pretty bulletproof. You don't have to worry about them that much.
And they're somewhere between free and very cheap in the scheme of things as well.
So sims are an awesome choice. Another type of motor you could venture into would be either 775 Pros or Red Lines. They're essentially the same motor for all intents and purposes. You get a lot more efficiency out of these motors, and that's in both your efficiency for power, but also a power to weight ratio. These are much smaller and much lighter motors. However, they run at 18,000 RPM with nothing on them. So they definitely require some sort of reduction, whether it's a gear or a belt. They also require a pinion to get pressed onto that shaft to be able to use, and they're prone to burning out. If at some point something gets stuck or it jams, you will end up burning out 775. So you just have to be ready for that if you sort of venture down this path.
Yeah, and then kind of the step up from this, and what you'll see top tier teams doing is using some of the newer motors, Falcons and Neos and things like that, because they again have an even higher power to weight ratio, which when you're pushing the envelope for what you can actually fit in your robot, power to weight ratio is key. And fortunately or unfortunately, price almost doesn't become an object at that point to some teams. And it's all about what you can squeeze the most effectiveness out of your robot. And so that's kind of, if you're at that point, you know, having a built-in encoder and things like that also start to make it a little bit easier. But yeah.
Now, how much power do you need? This is sort of the big ticket question that's very, very difficult to answer sort of beforehand, because it depends on a bunch of factors. Depends on the distance you're shooting. How many elements are you shooting a second? If you think back to like 2017, it was a big factor because you were shooting maybe 100 balls at a time.
What's popcorn machine of wiffle balls?
Yeah. What's your desired trajectory? Are you trying to really fang it at a flat trajectory, or are you going for a sort of a nicer curve? Often, if you can, generally an overpowered shooter is a more consistent shooter. So maybe how much overhead are you looking for in your power?
And definitely when you come to control systems, having extra power to play with is helpful, almost never a hindrance.
And then how much compression are you running, right? Coming back to compression, you run a lot of compression, you're going to need a lot of power to get over that. We've been doing this a while, so we can sort of take some guesses of good places to start. But the real advice here is prototype it. You're going to learn way more from a prototype than you are trying to calculate stuff. We've time and time again attempted to go through and do various calculations from physics in an attempt to figure out how many motors we need to do stuff, and inevitably the prototype ends up just being a much better way to answer that question.
And I would suggest, if you are erring on the side, go higher, kind of based on that overpowered comment. But also, if you're going to prototype, don't prototype with drastically more than you intend to use. And that depends on exactly what kind of the context is, what drastically means. But if you put 3 sims on your prototype, and then you're like, oh no, it's fine, I'll just put 2 on. You might think to yourself, that's 1/3 of the power. It ends up not being that. It ends up being a much more complex, almost butterfly effect of changes that can really mess with what's going on. So if you want to change the number of motors, change it in your prototype as well, so that you're not kind of getting bitten in the bum by underpowering your shooter when you change. I've heard that story many, many times from teams saying, I had 2 sims and I went to 1 because I thought I had too much, and then turns out 1 was actually 1/3, not 1/2 of the power.
So what are some good starting points from our experience? If you're using sims, you can often get away with 2. In this case, we're sort of talking about the vast majority of ball-shaped things, I guess, game elements we've seen. Exceptions maybe being 2014, where you might have to go with a bit more power for the massive exercise balls. But often 2 sims is a good place to start, which often gives you about 2 to 3 mini sims. Or 2 to 3 775 style motors.
I don't think anyone used a shooter, like a linear shooter or a hooded shooter. Oh, actually no, someone used a hooded shooter.
Yeah. But yeah, this is 9 times out of 10 a game element's going to be, or I guess a spherical game element has been around the same size. And this formula works pretty well.
And you can pretty comfortably say, you can look up previous robots of similar sized objects to try and figure out what people have been doing. You're always going to find hooded shooters, that's a guarantee. But look at some of the more mid-tier teams for ideas and inspiration rather than the top-tier teams, because typically there's a reason the top-tier teams are doing well with what they've done, and it's because it's hard and no one else did it.
So, and I think we'll come back to that point, because that was one of the questions. All right, next, you've picked your power. How are you transmitting it?
Yeah, so as I mentioned earlier, sims have a really convenient RPM, really convenient speed that works out when you have a 4-inch wheel. The linear speed of the wheel is really quite suitable for a shooter. So just direct driving that often is very effective. With the 775, sometimes, well, you're always going to need some reduction. That reduction is going to depend on how many of them and what kind of gearbox you want to use. So we've said here that versaplanetaries are adequate, fantastic for prototyping. To be honest, that's a really big hint here is, a single stage with a 3 that you can swap out to a 4 just to figure out what's going on. A fantastic choice for prototyping with a versaplanetary. But yeah, the limitation there is you can only have 1, and if you've got the budget, you can have 2 with that dual input.
It's getting a little dicey though.
Oh, the new one with the metal should be all right, but the plastic ones were really bad.
Yeah.
Like horribly, catastrophically failing.
But yeah, can't stress the point more that they're great for prototyping.
Yeah.
If you can or have the budget, slowly building up a small library of versaplanetaries makes prototyping so much easier. You have so many different ratios to test for shooters or intakes or sort of anything on your robot with those. So.
Yeah. A better solution is with belts and pulleys, where you can choose the right diameters to give you exactly the ratio you want. As we said here, great efficiency, but you got to get the tension right, and you kind of got to get once you picked your spacing, the options in terms of ratios are defined, and you can only stay within the belt size and the ratios. There's some calculators out there to help you with it, but it makes it more difficult to change ratios on the fly. And typically, yeah, the precision required in that hole spacing will lend itself to either some careful mentor supervision or a CNC.
Yeah, so it's certainly possible by hand, but it's difficult. You have to you have to be willing to put some time and precision towards it.
Yeah.
So this often lends itself well to a laser cutter or something like that.
Yeah, and then the chain, it's not really designed for going really fast. They are used, in applications where there's a high rotation speed, but that's a different kind of chain to what we see in FRC usually, and things like the amount of grease in there changes. Also, the tightness of that radius, of the pulley size that is going around, plays a big role, and we don't really have the opportunity usually in our shooters to have a gigantic 60-tooth sprocket in there to get a nice reduction that we might need. So it's more challenging. And yes, if you get the chance, look up how big a 60-tooth sprocket is. It's actually ridiculous they make them.
Yeah. So look, you can do it, and it will work, but usually we've seen that you end up causing yourself problems later down the line because either things aren't perfectly in line or there's more slack than you're expecting. Normal drivetrain or normal operation, you wouldn't see that, but when you start running chain this fast, it becomes a problem. So if you can, we'd recommend trying not to go down that path.
And I think also the chain is very inefficient in the scheme of things. And maybe the comment on efficiency more comes down to the power overhead. When your robot has lots of spare weight, you can kind of just put an extra sim in to get away from any of these problems. But if you're right on that edge of the weight limit, you're designing for the amount of power you need. So having inefficiency in your chain starts to become a real big problem.
All right. Next thing we want to sort of get into is a little bit of electrical. And really the only main point here is sensors. So maybe let's start off with, why do you need sensors on a shooter? The answer is generally consistency. The reason being is that the consistency of your shooter is very, very closely linked to how consistent you can hold a wheel at a certain RPM, and also how quickly you can recover to that RPM. And the only way to sort of get that is with some sort of sensor. You have to know how fast the wheel is going so that you can correct for it. We sort of laid out two solutions here. I am pretty sure all of you will have heard of the second solution, but I'm actually interested in telling you about a different solution that might be a bit easier. And it's a retroreflective sensor. So if any of you have used a tachometer, right, where you have a beam, you're shooting onto something that's spinning that you have to have either a line drawn or a piece of tape or something, that's essentially what we're doing here. We have a sort of retroreflective sensor. It's either maybe an LED and a light sensor or a little built-in package like what I've shown here. And all it's doing is measuring a piece of tape as it goes by. Or you can even maybe put some evenly spaced pieces of tape and do some math to calculate the RPM.
I think important thing to note here is we put simple and slightly harder. That does not mean slightly worse and slightly better. In most circumstances, with a good implementation, either are just as effective and going to give you, particularly for a shooter, just as good a results.
Yeah. So the retroreflective sensor is kind of interesting because it's really easy to mount. You don't have to be really precise at all in your mounting. As long as it's within some range where the light sensor can see the thing that's going by, Bob's your uncle. So in that case, they can be a really quick, simple solution that's reliable. It doesn't, I guess, respond poorly to things like vibration. And so it also works to really high RPMs. So it's sort of an interesting thing to consider, but definitely not the only solution. You can always use an encoder, which I'm pretty confident all of you will have seen at least once or twice before. And there are lots of options based on budget and availability and how they interface, especially for FRC. So, and they'll give you a bit more resolution than the retroreflective sensor and can technically give you position information, but largely those two often don't factor in with shooters.
Yep. It really doesn't matter that much.
Really doesn't matter that much. So they're a bit harder to mount because you have to be sort of directly on the shaft, and you have to be able to both manufacture, get a shaft that works with them and be able to mount the encoder with that. And they're a bit more sensitive to vibration. And the big one here is electrical noise. So a lot of the encoders that people use in FRC are what's called quadrature encoders, which talk over a line with a series of pulses in sort of simple terms. the faster you try to drive those pulses, the more it matters that your wires are shielded and your wires are short. Happy to go into this a bit more later, but the one thing you have to watch out with, especially quadrature encoders, is the higher RPMs, the more you have to pay attention to electrical noise. Yeah. A good suggestion here is one that I believe that they have in first choice. It's called the AMT103V. These are pretty good because they actually have little dip switches that let you change the pulse rate. So you can change the resolution, which is good because you can drive the resolution down when you want to do something very fast, like a shooter, or bump that resolution up if you're trying to use it for an arm. They're not quite as well built as some other encoders, but they're available locally. They're pretty cheap, and you get them in first choice. So I think they're a pretty good solution. They're also really versatile because they come with all of these nice little plastic collars that let you use them with a bunch of different shaft sizes. They're certainly easier to mount. So, nice. But generally, lots of options here. Just pay attention to, they'll generally have a max rated RPM. That's pretty important to pay attention to. And sort of the last bit you'll be thinking about in your design is the software. The important one here is your control system. So control system being, how do we take that sensor input and decide how much power to send to the motor? There's a solution I think you probably will have heard of called PID, but there's another solution I think is actually cooler and much simpler that can do.
Might have a go drawing that while you're talking.
Okay.
Also,
just don't draw up there.
Okay. I'll draw down here.
Yeah. So there's a really simple solution that I've come to know as bang bang, a bang bang controller. All it is it's sort of an if statement, and you say if your motor speed is less than you want, turn on the motor 100%. Otherwise, turn it off. And that's all the code you need to do it. It's really simple to implement. And you actually get relatively fast recovery. So when a ball comes through and slows down the shooter wheel a lot, your shooter will all of a sudden spike back up to full power until you get to the line. And so you get this sort of effect where you ping around your target line. And that's one of the only real cons with this is you can have some overshoot in your response. So you can actually solve this in hardware if you want. If you're able to add more mass to your system, it effectively acts as more of a damping effect and will help tune out that overshoot.
PID's too hard.
Yeah, I was impressed you're going to try to draw PID.
Good PID, you can't see it.
Yeah. So one of the only cons to this is, or the only other con I think, is that it's a bit hard on your components because you're sort of smacking it with power over and over again. The reason it's called bang bang is when you implement it, you often get this sound where your motor goes thunk, 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 thunk as it turns on, sort of on and off to keep it around the right area. It sounds a bit harsh and a bit crude, but it's actually can be a really easy way to get started.
Particularly if you have a fairly large range of like possible velocities. If you particularly if you're on a flat trajectory, it doesn't matter if you go faster. Like it's still flat trajectory. So
flat trajectory of the game element.
Sorry, yes. So the overshoot kind of doesn't matter. If you're trying to use an arc, this really will start to cause you problems, and that's where you get to PID. But I guess the ultimate takeaway of that is don't try and use an arc if you really don't have to.
Yeah. And then there's the sort of obvious solution, which is PID. You can use either the built-in library, or I would I really, really recommend using the PID that's built into the motor controllers. So they're built into the Falcon SRXs and the Spark Maxes and the Falcons. Might be a couple more that I'm forgetting. But generally built into the motor controllers, PID is really easy to do and much more consistent. And if
faster as well.
It's much faster, so it's less sensitive to timing. And it's the kind of thing where if you're willing to put the time into it, you can get really great results with PID. You get much more control over the response. You can make it more consistent, but it's also just difficult to implement and sensitive to timing if you're running it on the Rio. The next slide I'm going to blast through because I think it's very often a trap, which is vision processing. I know when I started in FRC, all I could think about was, man, we got to get this thing with vision. Vision, so it's the future, but it's very, very often a trap. Your driver will 9 times out of 10 be able to aim more consistently, And there's sort of these very few cases, at least if you're just starting out, where you might want it. And I think the one that I could think of was if you're in auto and you don't know the exact path of the robot. There's some chance the path of the robot might not be consistent. But 9 times out of 10, I would skip over vision.
Yeah. And the best bit about aligning to the field is you don't need any vision. And that's kind of the whole point. The other thing is vision will not only depend on the consistency of your shooter, but also then suddenly the consistency of everything else, particularly if you're trying to align using the drive base. You know, you got backlash in your drive belts, you got any kind of slipping of the wheels as you turn. So all your control systems start to become really important to be refined. And basically, if this presentation is for you, vision's not for you.
So I've stuck a couple options here. If you're interested in going down this path, feel free to reach out or to ask any questions. I can explain more about both of these, but largely would recommend sort of staying away from it.
Yep.
All right. Now we're up to the sort of quick and dirty way to do 2 different shooters. So you're doing your first shooter. What's the quickest sort of path of least resistance to a working shooter? Yep. First one, 2-wheeled shooter.
Yeah, so our suggestion is basically take a piece of ply that's sort of roughly the size of the game piece plus the wheels that you're going to use for the shooter, and drill some holes in that where the bearings are going to go, or you're going to mount the motor at the bottom. And then take some other wood, like a 35 by 90, and make some uprights, and then kind of a piece across the top there as well to support the other side of the shaft. So I actually quickly catted this up before the presentation to give you some sort of explanation. The other one.
Yeah. This one.
Yeah. So as you can see here, we just got the shooter wheels. They're some 4-inch wheels there with a shaft through and some hex bearings. And something simple like this is very easy to make, is fairly rigid, and it's going to give you some pretty good results. The key caution here for me is when you're prototyping, it is possible to go too fast with the wheel speed. So if you're starting to get nervous, potentially that is a good sign that you're going too fast. The other thing is the longer this shaft is, the more possibility there is for both bending, and then once it's bent, then the motion is eccentric around the axis and it accentuates that bending and starts to vibrate. So the shorter you can keep that, and in this case, you know, that's defined by the size of the game piece, but the shorter you can keep that, the better. And potentially consider in a final design using something other than a top brace so you can keep that shaft even shorter than that. But this is a great place to start with a 2-wheel shooter. Because it's fairly rigid as well.
Yeah. A couple of notes here. To drive these wheels, it's really easy to either do, you could just direct drive them with like a sim or something like that.
Yes, from the bottom, because then the seams become beautiful rests as well for your angle.
So you can do that. The other option is just stick bearings in these holes and maybe stick a belt out or something like that. You can test with something else. Another good option is like a versaplanetary here.
Yep.
The other sort of cool thing you can actually do with this is if you do have access to like a laser cutter, or you're particularly good at drilling holes, you can actually drill lots of sets of holes at varying levels of compression. And it gives you this really easy ability to pop this axle into a different set of holes and test different levels of compression really quickly.
Yep.
And going back, it's a really important question to be able to answer, and it's a really easy way to do it. So.
And also that change means you can really quite comfortably change one thing and one thing only. Okay, the top piece might actually need to be slightly different in this situation, but your variables are minimized, sorry, and that is pretty important for effective testing. And the hooded shooter as well, we got a suggestion that's a little bit more complex.
Yes, this is coming back to what we were saying about how the hooded shooter is just a little bit harder to sort of work with and prototype. But I think this is about the easiest way I could think to do it. So if you sort of start off with 2 bits of plywood and start off with them just like screwed together, because you'll need sort of 2 symmetric pieces here. What you're going to want to do is start off by drilling a bearing hole. I think I stuck this in the slides, but a kind of interesting note. a 28 mil spade bit often works pretty well for bearing holes if you're prototyping in wood, and they're not too hard to find. So we have a couple floating around the lab that are pretty useful when we're prototyping. So the first thing will be to drill a bearing hole, sort of anywhere. Once you've got that, stick a bearing in it with a hex shaft and grab a piece of string. And you could use that to sort of set a consistent arc going around that bearing hole. So I'd use this in this case to then sort of lay down some regular holes for standoffs. It's going to go between these pieces. Often we'll use churro. Andy Mark churro is pretty good because you can sort of just toss a 1/4-20 screw in the end. But just generally you need something to stand this off the distance of the sort of the distance of your game piece. Once you've got that and you have some standoffs going between these holes, grab just some piece of plastic, can be about 3 mil, drill holes in it and zip tie it to the standoffs. And you've pretty much got yourself there. You can stick some bearings in here, stick an axle across and whatever wheel you'd like. And you have yourself a hooded shooter prototype. Yeah. Now, as you can sort of see, this is definitely another one that benefits from laser cutting. You can do this really quickly if you have a laser cutter or some sort of CNC, but you can do this by hand. You just have to be a little bit careful.
Yeah. The rigidity of the system when you're testing a hooded shooter matters. Like, it's the most important thing when you're testing, essentially, because your compression will vary so wildly if you don't have a suitably rigid system. And that's one of the biggest factors in a hooded shooter. It doesn't matter quite as much in a linear shooter, but in a hooded shooter, it's like the thing that matters.
Yeah, compression being consistent.
And the other thing to note is we talked about this earlier between ourselves, but it might seem intuitive that you want some rails to run the ball along. Turns out you don't. Just believe us.
Yeah, every time I've tried this, I've thought, all right, I have this nice soft ball. I want some rails to keep it nice and centered. Every time I've tried it, it just doesn't work out. So if you can sort of think about the way it bends or it compresses around the rails makes it not very good. Or you can just trust this. It doesn't work very well. So yeah, a nice flat back plane is really good here. The other good thing there is if you're testing, you can actually test different levels of compression here by just putting more plastic in. Either put thicker plastic in or more layers, and you can use that as a way to test more or less compression. So if you design this with sort of less compression than you're expecting, and then just pop some extra sheets of plastic in to test higher compressions, it'll give you a pretty easy way to get to that number as well.
To be honest, you could probably get away with some like 3 mil plywood or something as your backboard as well.
Yeah, maybe. If
you don't have access to, polycarb or I don't know if you can bend acrylic that much, but yeah.
No.
Yeah, have something to have a think about.
Yeah, we often use either polycarb or you can get PETG, works well for this. And this is a similar idea where you can just stick a motor off the side and direct drive this. And then once you're starting to get a bit more advanced, you can hook up a belt to it or put a Versa here and put a couple motors into your Versa or something like that.
This is also another case of the warning, your shaft might bend. And particularly in hooded shooters, I don't know why it seems to happen more, but shaft bending is really bad.
Well, you're often pushing compression in a hooded shooter.
Yeah, true.
And so you'll be putting more stress on that axle and therefore putting yourself a bit more at risk.
And something that is kind of maybe obvious, but a tip to both students and mentors for safety is, when you're testing your first prototypes and you're not really sure of how robust they might be, make sure that you don't have anyone in the line of fire where it might spray out. So if you can see this view, you're in the wrong place.
Yeah, if you can see this view, or maybe you can see this view, you're in the wrong place.
Yeah, and just it can happen to anyone. We had a wheel explode on us during this season. So, and I tell you what, it scared everyone in the room. But by keeping everyone out of that line of fire, kind of like similar protocols if you were angle grinding or something, it's probably worth that little bit of inconvenience, particularly when you're prototyping with plywood when it might not be quite as robust as you'd expect.
All right, and I think that's the end of our sort of presentation here. We might go back to talking about trying to answer that original question that Luann had come up with.
about robots to look at.
About robots to look at, yeah. So, and this sort of actually helps answer the other question we got. The other really common thing we'll do at the start of the season is we'll look at the game element and rack our brains for what the most similar game element we've seen before is. It's a good example. When we saw the 2020 game element, these sort of yellow foam balls, I think all of us immediately said, wow, these look a lot like the Stronghold balls, and they look like they'll act a lot like the 2013 basketballs. And after that, often we'll just hop on the Blue Alliance and start playing Einstein matches. The videos from Einstein matches, just see what the good teams were doing and what really worked well for people. You can also then just start digging through matches at champs from maybe the divisions. Often you can find in some of the divisions teams that come up with a really simple design, a really easy to implement design that actually got them really far.
Yep.
And so it's really worth the time to have the students just start watching matches. You get a good feel for how the elements will act, how they sort of fly, how they get pulled up off either the ground or sort of intakes from wherever they were in that game, and then fired back out.
And watching sort of division elimination rounds gives you a really good feeling for kind of the speed that robots are going to be operating at, the cycle time, things like that. If you're watching Einstein matches, you just have to be really aware you are watching the best teams playing their best game.
Yeah.
So you're not looking at that being like, oh, they're going 20 seconds, maybe we can push that. No, you're looking at that going, they're going 20 seconds, we're going 50 seconds.
It's also important to know that a lot of the teams you'll see on Einstein generally have designs that look really simple, deceptively simple, but end up being much harder to implement than you think. There's a lot of work that's gone into those. However, from a conceptual design, if you sort of just stand back and look at from conceptually how they're doing, it can be a really good place to start.
And some of the simplest robots that do really well might not get to Einstein because those powerhouse teams are playing a slightly different game, but they're going to be getting into those sort of semi-finals in the divisions, or they're winning their local event, and so they're getting to champs at least. So you can get some really fantastic inspiration for nifty robots from that kind of division elimination kind of rounds. And maybe you're not looking at that alliance captain, but their first pick often is going to be a robot that does a task and does it really well. And I think that's something that for rookie teams and for developing teams, and look, even for ourselves sometimes, doing a task and doing it really well is more important than doing sort of everything meh.
Yeah, but certainly a motto that we like to live by is steal from the best and invent the rest. So if you can steal it, do so. It'll often work out pretty well for you.
So any other questions coming through?
I don't see any right now. So that was great. There was so much amazing information. I know the teams around Australia and around the world are going to love this presentation. So thank you so much. And I want to say a big thank you to Gordon for being there. Maybe he'll turn his camera on and give us a wave. Gordon was doing a lot of the backseat work in this. So thank you, Gordon. If there's no other questions, I think we will sign off for tonight.
Awesome. Thanks, Lan. Thanks, Gordon.
Thanks.
Don't forget, you can ask us questions through email or like other forums that exist that I'm sure Luann are going to be able to tell you about or has told you about in the past. So particularly in build season, feel free to reach out and we can give you some pointers or things like that on your shooters if you're having weird issues.
Yeah, definitely.
Awesome. All right. Well, thank you and good night. Okay, so I've ended the stream.